let's begin today. So it's been some time since we've discussed calculus because we didn't have a lecture on Monday. Instead, we're having it today. So last time we were discussing about maxima and minima as the application of differentiation. So let's take a quick recap of that concept and continue from there.
Excuse me, sir.
Yes.
Sir, did you tell us that maxima and minima was going to be in our major test?
Yeah, this is the basic concept of maximum minima. Right? The derivative is equal to 0 at the position of maxima and minima.
So because in the exam, like the sums were a bit tough, I guess.
You're finding the sums a bit tough. Okay. Doesn't
Yes,
matter. Like
and
when
I guess integration also came.
integration came in the test, it was not.
Sir, yes, integration was also there.
Yes, sir. 1-2 questions were there of integration also.
Okay, maybe there's some mix-up in the question paper. I'll check it out. Okay, I'll get those questions removed from the test analysis if that is the case. Okay.
Yes, thank you.
Okay. Yeah. So what we saw is that for a given function y equal to fx, if the derivative of the function dy by dx, if this derivative is positive in a certain interval. So interval means set of values of x, let's say x belonging to a to b. So that means the function is increasing in that interval because it has a positive slope. So as x increases, then y also increases. So we say that behavior of the function is increasing. So in that very interval, similarly, and if derivative of the function is negative, less than 0, in another interval, let's say x belonging to c to d or something, that means the function is decreasing in that interval. Whereas if the derivative of a function is 0 at a particular point, so if it is equal to 0 at a particular point, that means that the function has either a maxima or a minima at that point. So let us revisit this concept with an example. For example, I have the function I have this y is equal to 1 by x minus 1 by x square, and I am considering only values of x which are greater than 0. Okay. So now we have to find the interval in which the function is increasing then the interval in which the function is decreasing, okay, and any point at which the function y has a maxima or a minimum. So it can be maxima and or minimum. Okay. So what we do is we just follow the concept that we have discussed about, that given any function, we find out the derivative of the function, and then we find out that for what set of values of x, that is what interval of x, the derivative is positive, and similarly for what interval the derivative is negative. So accordingly, for those derivatives, the function is either increasing in nature or decreasing in nature. Whereas at certain points, if the function is having at a certain point or at multiple points, whichever be the case, if the function is having a derivative equal to 0, then it will have either a maxima at that point or a minima. And how we can distinguish that whether it is maxima or minima, that we can distinguish because we already know where the function is increasing and where it is decreasing. So at whichever point the derivative is becoming 0, we'll just analyze the function, in the whole interval, including that point. So we know that whether the function is increasing up to that point at the maxima and then decreasing after that, or is it vice versa? That is, the function is decreasing up to that point and increasing after that. So this thing is better understood with examples. Okay, so I will just work out this example in detail. So we'll just apply these concepts step by step in this.
Yeah, no scroll up, I have to write.
That portion bit is already there in last time's notes. This is a recap of what was there in last lecture. Okay, we've discussed this part in the last lecture. So you can take it down from the notes later. If you have any doubt in any of the concepts that I've listed out here, you can ask me straight away, but you already have this in the notes from last time, so you don't have to write it down in detail. Okay, so let's look at the application of this in this question now. So the function is basically what it is, 1 by x minus 1 by x square. So what we have to do is first differentiate the function, or so we can say that if this is a function fx, then the derivative of the function f prime x is going to be what? Differentiation of this term. Now what is differentiation of 1 by x? It's minus 1 by x square, correct? You just apply the x to the power n, and differentiation of 1 by x square is what? Minus 2 by x cube, correct? So this becomes 2 by x cube minus 1 by x square. So this is the derivative of the function. Whether we call it f prime x or we call it dy by dx, it's one and the same thing. This is the derivative of the function. Okay, so that's the first thing. We find the derivative. Now the first part, we want to find out the interval in which the function is increasing. Okay, so the function fx is increasing when dy by dx or f prime x, whatever we choose to call it, is greater than 0. Okay. So what is dy by dx? It is 2 by x cube minus 1 by x square. Okay. So that is how much now? It is 2 minus 2x, 2 minus x divided by x cube is greater than 0. Okay. Now remember, earlier on itself, for the function we have taken x greater than 0. We are only taking positive values of x. This was given in the question. Okay. So that means the denominator is always positive. Okay. So since x is greater than 0, so it implies that 2 minus x upon x cube is greater than 0 when 2 minus x is greater than 0, because already it should be less than 2. So that means x should be between 0 and 2. So this is the interval in which the function is increasing. Now this is telling me this. Okay. What it's telling me that the function fx is increasing from, or we can say it's increasing for the interval. You can write it like this, that x belongs to the interval. This symbol, as you know, it stands for belongs to. Okay. So x belongs to the interval 0 to 2, or you can say x is greater than 0, x is less than 2. Okay, so make a quick note of this part. So the thing is, see, this is a function whose graph we don't know from before. Okay. It's not a known graph. So there's no way that we could have guessed that for which values of x, y is increasing and for which value of x, y is decreasing. But now from the concept of derivative, okay, we are able to understand this, because you have any arbitrary graph of a function. You can see that at certain values of x, if the slope of tangent is positive everywhere, that means the function is increasing over there. Whereas at certain other values of x, if the slope of tangent is negative, that means shape of the graph is such that it's coming down. So what is the concept over here? That at any point where the function is increasing with respect to x, its tangent will be a line which has a positive slope, and vice versa. At any point where the function is decreasing, its tangent will be a straight line with a negative slope. So slope of tangent is nothing but the value of dy by dx. That is how we get this idea. Okay. So just make a note of the question and the first few steps. Go through it clearly. If there's any doubt in any of the parts, let me know. Whether
Sir,
it is the
sir, when you
tell me.
differentiate 1 by x, we cannot write it
Hmm.
as x minus 1.
We cannot write what beta as x minus 1.
Sir, 1 by x is x minus 1.
No, it is x to the power minus 1. It's not x minus 1. 1 by x is x to the power minus 1. When you bring x to the numerator, its power becomes minus 1. And that's how we apply the differentiation rule. No? Differentiation of x to the power n is what? It is n x to the power n minus 1.
Yes.
That's how we have got minus 1 by x1. No?
So you're teaching a new concept of interval, no?
I didn't get your question, Beta.
The last time you taught this interval,
Sorry?
that interval x is greater than x is between 1 and 2, like that type of sounds.
No, I'm talking about this particular question. In this question,
Sir,
how
I
will
am
we
talking,
find?
this
Yeah,
is a new concept you are teaching, that interval.
this concept I've taught, Beta. The question is new. The concept is listed for you above here also. Okay. So if the derivative of the function is positive in an interval, then the function is increasing in that interval. That is the concept. If the derivative is negative in an interval, then the function is decreasing in that interval. So now this particular question, we are applying that concept. Instead of a general function, we are given the function 1 by x minus 1 by x square with a specific range of x, or with a specific values of x which are given, that we have to consider only positive values of x, not 0 and not negative. So how will we work out the first part? That is the interval in which the function is increasing. We will apply that above concept now. That if the function's derivative is positive in an interval, then the function must be increasing in that interval. So given that function 1 by x minus 1 by x square, what we do is we find the derivative of that function and then substitute, then calculate the interval for which the derivative is greater than 0. So we have to find those values of x for which f prime x or dy by dx is greater than 0. So on doing this analysis, we get that interval, and that's what gives us the answer for the first part. Is it clear now?
So can you scroll down?
Yeah, scroll down. Let everybody write the steps down up to this step.
Sir,
Yes.
sir,
Yes. But I'm not able to hear you. I'm only hearing the word sir. What is the question?
sir, how 2 minus x are divided by x cube greater than 0 came?
That is what we are finding out. Now, let us see A part. What we are finding out, the function is increasing in which interval. So the condition for it to be increasing is that f prime x should be greater than 0. So what is f prime x? It is 2 by x cube minus 1 by x square. That should be greater than 0.
Yes,
But no,
sir.
we are applying the condition for this now. We are trying to find out the interval in which this condition is true. Okay. Now, what is the value of f prime x? Is this no? So we will substitute this quantity. This should be greater than 0. So that implies this statement. Got it now? Now,
Okay,
already
sir.
we are only considering those values of x which are greater than 0 because this is given in the question. So for every value of x that is greater than 0, your denominator is already greater than 0. So since x is greater than 0, when I'm saying this whole bracket is greater than 0, it means the numerator should be greater than 0 because the denominator is already positive. Okay, you understood the point now?
Yes, sir.
So f prime x कब positive होगा when the value of x is less than 2. But already we know that it has to be greater than 0. So it's between 0 and 2. Okay, so now from this, what we understand that even though we still don't know the proper shape of the graph, but we realize one thing that whatever the shape of the graph between 0 and 2, the function has an increasing nature. It must be going up. It must be rising. Now, what the value we don't necessarily know. Okay, but it's increasing like this. Whether it's negative or positive, we don't know. It might be like this also. But up to 2, it is increasing. Okay, so we'll do some more work and okay, but the graph is not the important thing for us just now. What is important is that we understand that in which values of x the function is increasing, and then later which values of x the function is decreasing. And of course, in between there will be a local maximum. Okay. So another way to visualize this is by just thinking of a number line instead of thinking of the graph of the function. Just think of a number line, which is like the values of x. Now this number line should start from 0 for us because we are taking only positive values of x. So for us, 2 becomes a critical point because the function is rising in this interval. It is between 0 and 2, the function is rising. Later we will see in just the next moment that from 2 onwards, the function starts decreasing. So that means at 2, it should be reaching a peak. Okay, so the function's graph should be something like this, that at the point 2, it reaches a peak. And after that, again, it starts decreasing. So I'll explain to you how that happens here. Okay. Okay, so A part is clear now.
Yes, sir.
Okay, so this is not important just now. What is important is that we have found the interval in which the function is increasing. Okay. Now B part, we have to just repeat the exercise, but with the reversed this thing inequality, because in the B part we want to find the interval for the interval in which the function fx is decreasing. What should happen? Its derivative f prime x should become less than 0. So it's the same thing, but I have to just reverse so the derivative was what, minus 1 by x square plus 2 by x cube. This was the derivative, or 2 by x cube minus 1 by x square, whatever. Okay, so this should now be less than 0. So 2 minus x by x cube should be less than 0, and x is anyway greater than 0. So it implies that 2 minus x should be less than 0. That means x should be greater than 2. So now this is showing me that, okay, from x 2 to infinity, in fact, because so therefore for the interval x belonging to the interval 2 to infinity, what is happening? The function is increasing. Fx is increasing. Oh, sorry, fx is decreasing. My mistake. Derivative is negative. So fx is decreasing. So now that we have the complete information, we know that between 0 and 2, fx is increasing. And we also know that between 2 to infinity, fx is decreasing. So now we can think of a more proper number line. So our number line for x is from 0 to infinity. But in between 0 to infinity, the function is increasing in this part, and then after that is decreasing in this part. Up to 2, it is increasing, and then after 2, it starts decreasing as x goes to infinity. So this is the extra information that we're getting from this thing, from the algebraic sign of the derivative. Right, so this is clear to all of you? Okay.
Yes, sir.
Now we see, so see, for the third part, it becomes obvious, if the function is increasing up to 2 and after 2 it is decreasing all the way to infinity, then at 2 what sort of point it should have? It should have a peak point, no?
Yes, sir.
Yes, sir.
Okay, so since fx is increasing, I'll write this short form for increasing from 0 to 2, okay, and then decreasing from 2 to infinity. So it's obvious over here. I don't even need to do this, find the derivative equal to 0 and all that. It is pretty obvious here that the function has a peak, or what we call a local maxima. Now, in language of calculus, a peak point in the graph is called the local maxima. Sorry? At x equal to 2. Yeah. Now, you can also see that the derivative of the function f prime x, which we just saw, is minus 1 by x squared plus 2 by x cubed, or 2 minus x by x cubed. So this derivative is equal to 0 at x equal to 2. So as expected, that at the point where there's a peak point or local maxima, the derivative of the function is 2. So now we're getting all this information about it. Okay, that at x equal to 2, there is a local maxima point. Or what in simple language you can call, there's a peak point in the graph. So there's a local maxima at x equal to 2, whereas the function is increasing before 2 and decreasing after 2. Okay, so this completes the question as far as we are concerned, because this is the only analysis we were asked to do in the question. But now that we have this analysis, actually we can go a little bit further and we can actually try and plot the graph of the function. Okay, so let's do that. But remember, this graph plotting part is like, it's something that takes more experience in mathematics, right? And many of you are not going to be students of maths because you are PCB students. So it's not something that you are expected to do at the exam level. It is just for your understanding, the graph plotting part. For our physics application, what is important, that we should be able to find these three things over here for this function, that in which interval the function is increasing, which interval the function is decreasing, and then again at which points the function has maxima and minima. So that we've already done. But some extra information now that we can get from this about the function. So let's try and visualize the graph of the function. So what was the function again? It was 1 by x minus 1 by x square, and we were strictly taking values of x which are greater than 0. Okay. Now, can you tell me what is the value of the function at x equal to 1? What is the value of y? You can see that it's 0. Okay. At x equal to 1.5, what is the value of y? You can see it is 1 upon 1.5 minus 1 upon 1.5 square. So that's like 2 by 3 minus 4 by 9, right? So that becomes how much? 6 minus 12. So 6 minus 4 by 9. So that is 2 by 9. So the value of y is 2 by 9. Okay. Then check at x equal to 2. What is the value of y? Y is equal to 1 by 2 minus 1 by 4. So that will be 1 by 4, or 0.25. This will be approximately 0.22. Okay. Then let's check at x equal to 2.5. What is the value of y? So you see that y becomes 1 upon 2.5 minus 1 upon 2.5 square, which we can write as 2 by 5 minus 4 by 25. So that's becoming how much? 10 minus 4 by 25. So it's 6 by 25. So that is approximately 0.24. Okay, like this. Similarly, at x equal to 3, we can check. So I'm just taking some arbitrary values. It's 1 by 3 minus 1 by 9. So that is second 2 by 9. 0.2. Okay, now let's take some slightly more extreme values, like take x equal to 10. Now see what y will become. 1 by 10 minus 1 by 100. So that is like 0.9 minus, sorry, 0.1 minus 0.01. So that is
0.09.
0.09. So y becomes 0.09. Now similarly, check at pretty large value, like let's say 10 raised power 3 or 1000. So what this becomes? Y becomes 10 raised power minus 3 minus 10 raised power minus 4. So 0.001 minus 0.0001. So it becomes 0.0009, right? Now let's take quite a ridiculously large value. Like let's take 10 raised power, like let's say 10 or something. So you will see that y will be nearly 10 raised power minus 10. It will be in fact something even smaller than that. So it's very close to 0. No? 1 upon 10 to the power 10 is a very small number. Okay. Now similarly, let's take closer values to 0 also on the end. Now, we started from 1. Let's take x equal to 0.5. Can you tell me how much y is? Just take some values, okay? And take x equal to 0.1 also. And tell me how much y is. And also take x equal to very close to 0. So like very small number, like 10 raised power minus 5, and see what y is. So just do these three calculations and tell me how much is y when x is 0.5, then again when x is 0.1, and when x is 10 to the power minus 5. So you see something very interesting here. Just work these three values out and send it to me in the text message. You should be getting -2. Anybody getting this?
Yes, sir.
Yeah, beta. Very good, Sanvi, that's correct. Okay. What about when x is 0.1?
-90.
Yes, very good. -90. So it's becoming a large negative number, no, comparatively. You can see x is a pretty small number, 0.1, and y is a pretty large negative number. It's like -90. So now you'll see the trend how it goes when x becomes very small, like 10 raised power -5. So that is 0.00001. So see what happens to y at that stage. Something very interesting here will happen. You can give me an approximate answer also. It doesn't have to be exact.
Sir, -2.
Minus that you're seeing for 0.5, no, beta?
Yes, sir. Yes, sir.
Yeah. Okay. Complete all three and send me in the text message. Those who have finished the first two, just work it out for 10 to the power minus 5. Yes, very good. That's correct. Okay. Sad, it's correct. So basically, see, when x is minus 5, no, because 1 by x square is in the denominator with a minus sign, y will tend to become like, it will almost be equal to minus of 10 to the power 10. So that's a very large negative number. Okay. So this is a extremely large negative number. Okay. So by extremely large, we say it's like almost tending to minus infinity. So it's such a large number, 10 to the power 10 with a minus sign. Whereas just like over here, 10 to the power minus 10 was a very small number, so it's tending to 0. So you see this range of as x is going from something very close to 0. There's almost x is almost tending to 0. So y is tending to minus infinity. And on the other side, when x is tending to infinity here, because 10 raised by 10 is a very large number now. What is y tending to is tending to 0. And in between, you can see that at 2, there is the local maxima. So local maxima point has the value of x equal to 2 and the value of y equal to how much? 1 by 4 or 0.25. Okay. And we also had this significant point that at x equal to 1, the value of y is 0. Now I'm going to use these points as a guideline to sort of estimate what the graph of this looks like. And you'll see that it's a very interesting shape. And you will see how it justifies what we had got in the part ABC earlier of the question. That why the function is increasing from 0 to 2 and then decreasing from 2 to infinity. And therefore at 2, it has a peak point or it has a local maximum. So, if you use a graphic software to plot the graph, this is what the software actually does. It has a program that writes not just 10 or 12 values like we've written, but literally hundreds of values because it can calculate very fast. And then it plots those values on a two-dimensional screen. So it gives you a very accurate graph. Okay. So we don't have that much time and we don't require that kind of accuracy. We just want to understand the behavior of the function. And you will see how accurate the behavior of the function we get just by using those three concepts. That derivative is positive where the function is increasing, derivative is negative where the function is decreasing, and derivative is 0 at all turning points. That is either the peak points or the dip points. So in this case, there is only one peak point. Okay. So this is a bit of an advanced type of application of calculus of differentiation, but it is very much required for us in certain physics problems. Okay. So we are learning it over here. Okay, so I hope the set of values is clear to all of you now.
Yes, sir.
Okay, so now let's see how we can put this information together in a graphical form. Okay. So in this problem, remember, we are not plotting the negative x part. We are only plotting x greater than 0. So I will not plot the negative x side of the axis. So you'll notice that some of our data points, of course, the point 0 itself is to be avoided because we are taking only x greater than 0. But we did get something that when x is tending to 0, okay, then y is tending to minus infinity. Like we had got that when x is 10 raised power minus 5, y was becoming almost equal to minus of 10 to the power 10. So that means, when you come to a point which is very close to 0, the value of y should be like somewhere very far down. And from there it is increasing. So this graph will look like this. It's increasing. It crosses this point at which point 1. Because we had seen that at x equal to 1, the value of y was 0. It continues to rise up to 2. Okay. So it kind of peaks at 2. And then after that, it starts dipping again. Starts decreasing, which you can see in the values that we plotted also. So much so that by the time x tends to infinity, y has become almost 0. So if I draw the graph more accurately, like a very smooth curve, which I'll struggle to do here, but nonetheless, I should get something that is coming very, very close to the x-axis. So that by the time x tends to infinity, y tends to 0. That is when x was 10 raised power 10 we had seen, y was, it was how much? It was this one. Y was tending to 10 raised power minus 10. So that kind of thing. So you can see that at this peak point, the value of y, that also we had calculated, was how much? It was 0.25. And for example, we had also seen other points that at 1.5, we had seen the value of y. Then, for example, at 0.5, we had seen the value of y. So we can compare some of these also. Okay. And again, we had seen at, I don't remember which points, 2.5, I think that was another point we had seen. Yeah, so at 2.5, it was 0.24. Okay. And at 3, it was 0.22. So this value, it goes and repeats itself at 3. 0.22 like this. Okay. But anyhow, you can see that what is happening here, that at x equal to 2, if we draw a tangent line, it has 0 slope. So at x equal to 2, slope of tangent equals to 0. Whereas if we draw a tangent anywhere between 0 and 2, you can see it will have a positive slope, whether we draw it here or here. Okay, so x belonging to the interval 0 to 2, you can see that slope of tangent is positive. And if you draw a tangent anywhere after 2, so whether that is here or here, you can see that it has a negative slope. It becomes more and more flat, like parallel to the x-axis, but it's still negative because y is decreasing. It's tending to 0 as x tends to infinity. So for the x belonging to 2 to infinity, the slope of the tangent is negative. And you can also see that at x equal to 2, there is a peak point. That peak point's coordinates are 2, 0.25. The y coordinate is 0.25, the x coordinate is 2. So this question was just to demonstrate to you that even if you have a function which otherwise looks a little tricky, that there's a 1 by x term, there's a 1 by x square term, so it's not something like an everyday function like a simple quadratic function or a simple cubic function, not something like that. It looks fairly complicated, but just by using this information about derivative, okay, that f prime x is positive in certain interval, f prime x is negative, and f prime x is 0 for turning points, we can already get an idea about how the graph of that function should look. If you actually use a graph plotting software to plot a very accurate graph of this function, you'll see that the shape of it is more or less like what I've drawn over here. Okay. There might be differences in curvature, the shape might be more smooth than how I've drawn it, but the behavior of the function is going to be exactly like this, and these points are accurate. The points that we have plotted above, they are accurate. Okay. So this is the full scope of differentiation. Okay. However, as I told you that we won't require all this in physics, graph plotting and all this will not be required. We will just be needed to do the kind of solving that I have given in that question. the ABC part. Those kind of things we should be able to work out. Okay, so this will require a bit of practice. So we're going to do a couple of more questions in the class before we move on. So next example, I'm going back to quadratic function, something easy for you to work out yourself. So we have this function y is equal to 4x minus x square plus 1. Okay, so we have to find the interval in which y increases with respect to x, and similarly find the interval in which y decreases with respect to x, and then we will also find local maxima or minima, if any, and we will also plot an approximate graph. Just an approximate graph we plot. Okay. So don't worry if you're not that confident about the graph plotting thing. It's not that essential, as I told you. It is just for your understanding. But this you have to understand how to work out the ABC part over here. Just try this out, people. Will discuss in a bit. Now, see, in this function, there is no restriction on x. In the previous function, the question itself had said that there is a restriction on x, that we are only considering the positive values. Here, we are not saying anything like that in the question. That means my value of x can be anything from minus to plus infinity. We have to consider all possible real number values of x from minus to plus infinity. So just repeat the same steps of the previous question in this, and you'll see this question is much easier because it's a quadratic function.
Excuse me, sir.
Okay, very good. I have received a lot of answers. Just keep one thing in mind here, that there is no restriction on x being positive. So yeah, Sanvi, your answer is correct. Yes, very good. A and B both parts are correct. Good. Anybody else has worked it out? Okay. Let's see here. So what we are doing is, first step, given the function y equal to fx is 4x minus x square plus 1, we will find the derivative of the function dy by dx, or f prime x is differentiation of this. Okay, so take the differentiation operator inside. So 4 minus 2x plus 0. So that's my derivative. I can take 2 common also and write it as, this is my derivative. So now I'm ready to analyze everything. So for example, in the A part, okay, y increases with respect to x when f prime x is positive. So that implies that 2 into 2 minus x should be positive, which means that 2 minus x should be positive, because obviously 2 is a positive number. So that means x should be less than 2. So x less than 2 here means that there is no restriction on x. So less than 2 means less than 2 all the way to minus infinity. Okay, so for this interval, the function has this behavior, that it is increasing. So likewise, you can see that y is decreasing with respect to x when f prime x is negative. So here you get x is greater than 2, which again there's no restriction on x. So greater than 2 means greater than 2 all the way to infinity. So 2 to infinity, this interval now, the function has this behavior, that it is decreasing. So it's pretty obvious that at 2 the function should have a local maxima again. So therefore, dy by dx is equal to 0 at x equal to 2, because dy by dx is this. So at this point, there is a local maxima or a peak point. So just make sure you understand all this information and try to visualize the graph. Now we will discuss. It's very good,
Sir?
Sanvi. Correct. Yes.
So I
Yes,
have a
but
doubt, like it is like always necessary that y will increase with respect to x when f prime x is greater than 0.
yes, it is necessary. Why? Beta, देखो, see, f prime x is positive का मतलब क्या है? The slope of the tangent is positive. So you think of any curve, when the curve shape is such that when you draw the tangent, it has a positive slope. Only when the function is increasing. If the shape of the curve is like this for a decreasing function, that at any point, what about the slope of the tangent? It will be negative, no?
Yes, sir.
Understood, no? So the moment we understand that for certain values of x, f prime x is positive, we understand that definitely for those values of x, what is happening? Y is increasing. It cannot be decreasing, because the slope of the tangent is positive.
So, sir, they will give like slope of the tangent is positive or negative.
That is the same thing as saying f prime x is positive or negative. You understand? So we want to find that interval where f prime x is positive, because in that interval fx will be increasing.
So you are not audible properly.
Okay. But the audio is like clear from my side. Yeah. So what I'm saying is that if f prime x is positive, it automatically means that slope of tangent is positive, no?
Yes, sir.
So that's what we have done in A part. Now we want to find the values of x where y is increasing. So we're just solving for the condition that derivative or dy by dx should be positive. Because in those parts, the tangent will have a positive slope, so y will be increasing.
Yes, sir. So the f prime x is positive. That's why y is increasing when f prime x is greater than 0.
Yes. Similarly, when f prime x is negative, it means that the slope of tangent is negative. Na? So the function must be decreasing.
Yes, sir. Understood.
Sir,
Yes.
sir, in A part, x is decreasing, no? So why it is maxima?
No, it is increasing up to 2, na? From minus infinity to 2, the function is increasing.
So how you are taking minus infinity to 2?
Because I have solved this condition. Na? See, I solved for f prime x being positive. So what I got? 2 minus x should be positive. That means x should be less than 2, na?
So
So
means
less than 2.
you are taking the value of x where this equation becomes 0, no?
Which equation, beta? Which equation you
The
are saying?
2 into 2 minus x.
It's 0 at 2, beta. It's not 0 for x less than 2. So that's why, see, we are talking about less than 2. When x is less than 2, what is this quantity 2 minus x? It's positive, na?
Yeah, no,
So you're understanding the function is increasing here, na? Because up to 2, the derivative is positive, na? For this part, for x less than 2, the derivative is positive. X ka koi bhi value le lo which is less than 2. See, you can take x equal to 1, you can take x equal to 0, you can take x equal to minus 1, you can take x equal to minus 100. For all these values, the derivative is positive. So the function
Yes,
is
sir.
increasing. Whereas for any value of x which is greater than 2, you can see that the derivative is becoming negative. That means the function is decreasing. That means the shape of the graph must be like this, right? It must be peaking at the point 2.
Okay, sir. Understood.
What? Understood? Okay. So we can see that it has a local maxima at a peak point at x equal to 2. Okay. Now for the graph part, we can do a bit like this. So what was our function? It was 4x minus x square. So you can see that at x equal to 0, the value of y is 0. At x equal to 1, for example, you can see the value of y is how much? 4 minus 1 or 3. Okay. Then at x equal to 2, the value is how much? 8 minus 4. So that's 4. Okay. Then at x equal to 3, you can see the value is 12 minus 9. So that's again 3. Then at x equal to 4, you can see the value y is becoming 0. At x equal to 5, it will become a negative quantity. It will become 20 minus 25, so minus 5. Okay. Now, for example, if I take x equal to 6, y is 24 minus 36, so that is how much? Minus 11. Like that, if I take a pretty large value, like x equal to, let's say, 10 raised by 3, then y will become a very large negative quantity. It will become minus 9,000 plus, sorry, minus, so it's almost, minus of 10 raised by 6. So it's a very large negative number. Okay. So when x tends to infinity, you can see that y tends to minus infinity. Okay. Similarly, if you start taking values of x which are less than 0, so you see at x equal to minus 1, y's value is becoming minus 4 minus 1, right? So that's minus 5. Then x equal to minus 2, for example, y is becoming minus 8 minus 4. So that's minus 12. Now let's start taking some larger values. X equal to minus 10, for example, y will become minus 40 minus 100. So minus 140. Okay. Now take like something pretty large and negative, like minus 10 raised by 3. So you see that y will tend to almost be equal to again minus of 10 raised by 6. So again, when x tends to minus infinity, y will also tend to minus infinity. So this, and the rest of the things that we've drawn here, we've written here, all this together will show you that the graph of this function is ultimately looking something like this. Yes.
But in x equal to 6, y should be minus 12, not minus 11.
Is it? Okay, I'll just check. Yeah, I'll make the correction. Just a second. So see that this graph has somewhat this kind of a shape. In between at this point, it reaches the peak 2. And the value of y at the peak was how much? It was 4, right? And again at 4, it was becoming 0. Now I'm not plotting all the other points, okay, but you can put them in and you'll understand why the behavior is like this. Okay. Yeah, this was how much? This was minus 8 minus this one you were saying x equal to minus 2.
Equal to 6.
Oh, x equal to 6. Okay.
Should
So
be
that
minus
is 24 minus 36. Yeah, correct. Minus 12. Should be minus 12. Yeah. So for example, some of these points you can plot in that graph also. You can see that at x equal to 3, the value of y was becoming something. So the same as 1. And for example, at 5, then at 6, you can see the values were at 6, it's a pretty large negative value, minus 12 like that. Okay. So this roughly gives you an idea of the graph of this function. So as I said, plotting the graph is something more complex. It will require an application of few more advanced things in advanced calculus, which you will study in maths. Those of you who are doing the PCM course in 12th. So maybe not so important for us over here, the D part. Okay, what is more important is the first 3 parts, that we should know how to calculate the intervals where the function is increasing, decreasing, and where it has local maximum, minimum, etc. So I will just take you through the solution once more. Just note down the key points.
So in D part, why you remove +1 from the equation?
I remove what would I? I've not removed +1.
Plus, you wrote y is equal to 4x minus x square, but above in red you wrote, yeah.
No, uska derivative beta. Differentiation of 1 is 0 na. Next step we are differentiating that. Okay. In this I have not added the 1. Okay, my mistake. Yes.
Sir.
In D part you're saying, no? This one, yeah. So
Yes.
all these values will actually be 1 more than what they are. Okay. So we'll have to change the values. These will all become like, this will be 1. This will be 4. This will be 5. This will be back to 4. Okay, then this was again going to become 1. This will be minus 4. This will be minus 11 instead. Even these will be minus 4 and minus 11. Forgot to add the 1. Minus 139. So the graph will change a bit. Okay, I'll do the correction to the graph. Okay. Just first make sure all of you are clear with these steps. Go through them once, write down the key points. If there's any doubt, just let me know. So we'll just make a slight modification to the graph below. Just first write down some of these values. Okay, so what we'll have to do here is in this graph, I just bring down the x-axis a little bit. It will solve the problem. But before that, okay, I'll just replot the graph. There's no point here. See that the graph shape is something like this, where at 0 its value was 1. At -1, the value of y became some negative value, which I had written over there. It was -4 or something. But once again, where is the maxima? It is at 2. The value of the maxima is 5. Whereas, for example, at x equal to 2, sorry, x equal to 1, the value of y was 4. And then that again repeated itself at x equal to 3. Whereas at 4, the graph is not exactly drawn to scale, but see that. Something like this, the graph is of this function. So again, this point here, this is the peak or local maxima point. Okay, so this is about maxima and minima. We will do, now we will see a question in which the same function has multiple turning points, or it has both maxima and minima. So next example, let's take a little bit more complex. Now we have to find and the intervals in which y increases or decreases with respect to x. So we will do the same treatment to this function, but because it's a cubic function, it's going to be a little bit more complex. So given the function x cube minus 3x square, the first step is to differentiate it and find the derivative. So derivative of the function is differentiation of x cube minus 3x square. So that is 3x square minus 6x. Okay. So we can write the derivative by doing a bit of factorization here. I'll write it like this. So now we can see that at a point of local maxima or minima, derivative of a function must be 0. So here, so that gives us 2 points, x equal to 0 and x equal to 2. So now there is either going to be a case like this, that either local maxima is at x equal to 0 and local minima at x equal to 2, or it is possible that local maxima is at x equal to 2 and local minima is at x equal to 0. So which of these two is happening, we have to find out. Okay. So for that, we'll talk about the intervals. Okay. So note this down first and then try to work out this part, that intervals in which y is increasing or decreasing. So that will make it clear that out of these two, which one is happening. Is the function having maxima at 0 and then minima at 2, or is it having minima at 2 and then maxima at 0?
Sir,
Yes, people, you have calculated.
so,
Yeah.
so, can you read the line which you have written under either?
Either local maxima is at 0 and local minima is at 2, or inverse of that. That local maxima is at 2 and local minima is at 0. Now, these are the two possibilities. Either the shape of the graph will be like this. No? So the maxima point is coming at x equal to 0 and the minima is coming at x equal to 2, or it's the shape of the graph might be like this, that the minima is at 0 and the maxima is at 2. So which of these two graph shapes is happening over here for the function? We have to find that out now. Okay, this is clear, huh? This would be case 1. This would be the shape of the graph in case 2. Okay, so for that, to find out that which of these two graphs is the case, we need to actually answer this question, that in which interval y increases and in which interval y decreases. This was what we had so far. So now fx increases when f prime x is positive. So that means this quantity 3x into x minus 2 should be positive. Now see, you have two terms over here, x and x minus 2. If we say that the product of two numbers is positive, what it means that either a and b are both positive, okay, or it would also be that a and b are both negative, because the product of two negative numbers is also positive. No? So either it means that x is greater than 0 and x minus 2 is greater than 0, or it means that x is less than 0 and x minus 2 is less than 0. So x minus 2 is greater than 0 means what? X is greater than 2. Okay. And x minus 2 is less than 0 means what? X is less than 2. So this condition that x is less than 0 and it is also less than 2, it basically means what? X is less than 0. That is when both these quantities are negative. And this condition that x is greater than 0, but at the same time x is also greater than 2, here it means what? X is greater than 2. Okay. So that means the function, or that means f prime x is greater than 0 for x belonging to either minus infinity to 0 or x belonging to 2 to infinity. That is, x is greater than 2 or x is less than 0. Okay. Another way to understand this is, see, here it's the product of two terms, x into x minus 2. So think of a number line of the values of x. Now think of the quantity 3x. For 3x, whenever x is less than 0, 3x is a negative quantity. Whenever 3x is greater than 0, 3x is a positive quantity. Now similarly, also think of the quantity x minus 2. Now for this, the important point is 2. Whenever x is less than 2, x minus 2 is negative. Whenever x is greater than 2, x minus 2 is positive. So now what we can say about the product of these two terms, 3x into x minus 2. So in the region where x is greater than 2, the product is plus into plus, so it's positive. In the region where x is less than 0, it's minus into minus, so again it is positive. And only in the region between 0 and 2, it becomes negative. So likewise, we can see that fx is decreasing when f prime x is negative. So that means 3x into x minus 2 is less than 0. That means x belongs to the interval 0 to 2. So now, again thinking of this number line, if we are talking about the function fx, we can see that the derivative is positive here, so the function must be rising in this region. Then the derivative is negative, so the function must be decreasing in this region. And then again, the derivative is positive, so that means the function must be increasing. So the graph of that function is looking like this. It has local maxima at x equal to 0. It has local minima at x equal to 2. Okay, so for quadratic functions, this analysis is very simple. For cubic functions, it's a little bit more complicated, but this is how we do it. Okay, so just make a note of this fully. So this is the second part of the question where we have analyzed the intervals where the function is increasing or decreasing. So we are seeing that the function is increasing in this interval. The function is increasing for this interval. Whereas you can see here that the function is decreasing for this interval.
So what is the answer for A part?
Yes, A part answer now, if you go back to that, you can see that the function has a local maxima at x equal to 0 and local minima at x equal to 2. You can see in the graph I have drawn below, the rough graph. There's a peak point at 0 and there's a dip point at 2. Is it clear?
Sir, how did you get that maxima at 0 and minima at 2?
F prime x का range देखना कहाँ पे negative है और कहाँ पे positive है. So the function is increasing from minus infinity to 0. Then it's decreasing from 0 to 2. So obviously at 0 it will have a peak point. No?
Yes.
That's how I understand.
Okay.
Okay, people. So this question is clear. Okay. Okay. Now so this is about maxima and minima. Now in the ending part of today's session, we'll take a brief introduction into integration. The second part of calculus. It's very easy actually because integration is like just a reverse formula of differentiation. So we have done so much of differentiation by now that integration will be very simple for us to understand. So integral calculus or integration is the next operation that we'll study. So this particular symbol, this is the symbol used for integration. Okay. Just like this particular symbol was the symbol for differentiation. Like that, this symbol here means symbol of integration. So for example, if we are writing the symbol like this, it means we are doing integration of sin x, okay, with respect to x. Just like if we write d by dx of sin x, that means we are doing what? We are doing differentiation of sin x with respect to x. So like that here, it means integration. So the general symbol that we use for integration is like this. Integration of any function f with respect to the variable x. So this statement means we are doing integration of the function fx with respect to the variable x. So just make a note of the symbol first. I'm not giving you the definition or the formula yet. It is just the symbol so far. What this symbol means, it means that we are doing integration of whatever we have written to the right of the symbol. We are doing integration of that function. So if we have written integration of, let's say, x square, that means we are doing, this is integration of the function x square with respect to x. Or if we have written
Sir?
integration of root x, yeah, tell me.
So what is the use of writing dx?
So that we know what is the variable of integration, with respect to which variable we are integrating. You understood the point? No?
Okay, sir.
Like in differentiation also, why we write the dx in the denominator? We could have just written d in the denominator. Is to understand that the variable of differentiation is which one? X. So here we are differentiating the quantity inside this bracket, whatever we are writing over here. This quantity is being differentiated with respect to what? X. So like that, when we write integration, there is some quantity here, but into dx. So that means the variable of integration is what? Dx. Whereas if it is some quantity into dt, then we are integrating that quantity with respect to t and not with respect to x. So it is to tell us what is the variable with which we are integrating, with respect to which we are integrating. Is it clear?
Okay, sir. Yes, sir.
So
Yeah. Okay, understood this one. Now the next thing, see, once you understood this is just the symbol. We haven't understood anything about integration yet. So we come to
So,
the meaning of, yeah.
I was writing.
Oh, okay. Wait. Okay, tell me when you're finished with it.
Done, sir.
Okay. Okay, now let's see what is the meaning of this operation. What we are trying to do when we integrate. Like we had seen, the meaning of differentiation was what it was, rate of change. So there are two types of operations in integration. So the first type of operation, so we'll say that these are so we do two types of operations in integration. The first is called indefinite integration. So the purpose of indefinite integration is operated on a function, let's say fx, to find something called its antiderivative. So every function has something called an antiderivative, which we usually write with the symbol ix. And indefinite integration is the operation that gives us the antiderivative. So integration of fx with respect to x, the output of that operation is another function which is called the antiderivative. So here, this statement that we've written below, it will be written as indefinite, or it will be read as indefinite integration, or in short, we can just say integration of fx, obviously with respect to x. Now, what it is giving us, it is giving something which is the antiderivative of that function fx. So now let's understand what is the meaning of antiderivative. So if ix is the antiderivative of fx, it means that when I differentiate this function, what I should get should be fx. So we'll understand this with an example, then you can note this now. So for example, we know that differentiation of x square is how much? 2x. So that means 2x. Sorry, that means, so yeah, if we say that way, we'll say 2x is the derivative. Is the derivative of x square. So if 2x is the derivative of x square, what it means is that x square has what relation with 2x? It is the antiderivative. If 2x is the derivative of this, that means x square is what relationship with respect to 2x? X square is the antiderivative of 2x. Because 2x is the differentiation of x square, that means x square is the antiderivative of this. Okay, so in symbols, what it means that the moment we are saying that differentiation of this gives me this, that means the reverse of this, that integration of 2x with respect to x, that should give me what? X square. If differentiation of ix is equal to fx, it means integration of fx is equal to what? Ix. Okay. So that is the first type of operation that we are learning in integration. It is something that gives us something called antiderivative of a function. So what antiderivative means? It is like the reverse process of differentiation. That if ix is the antiderivative of fx, that means fx comes from the differentiation of ix. If 2x is the derivative of x square, that means x square comes from the integration of 2x, or x square is the antiderivative of 2x. If a is the derivative of b, that means b is the antiderivative of a. This is the meaning of this term.
So, sir,
Yeah.
so integration of cos x would be sin x.
Yes, very good. Because differentiation of sin x is cos x. So that's very correct. Okay, if I know that differentiation of sin x gives me cos x, so that's as good as saying that integration of cos x gives me sin x.
Done, sir.
Sir, wait, sir.
Okay.
So completed.
Okay. Okay. Now see the general formula that we'll get for integration here, for indefinite integration. Is that integration of x to the power n, where n is any real number, is given by the formula x to the power n plus 1 divided by n plus 1 plus c. Now I'll explain all these terms. Okay. So where n is any real number with one exception, we have to rule out -1. For -1, this formula doesn't work, because if you take capital N as -1, on the right hand side, the denominator becomes 0. So that's an undefined operation. So we can't take the value of n as -1. Okay. And what is c? C is basically called the constant of integration. Which is basically a constant of any real number value. Now I'll explain why this constant comes also. Okay. So let's just understand this with an example. So let's take n equal to 1. So what we'll get? Integration of x. So according to this formula, it should be this. Okay. So it should be x square by 2 plus c. So now what is the meaning of this operation? That if I'm saying integration of x dx is x square by 2 plus c, it implies that differentiation of x square by 2 plus c should be how much? It should be equal to x. So you can see it will be equal to x, because differentiation of x square by 2 plus differentiation of a constant. Okay. So differentiation of x square by 2, half comes outside. Okay. And differentiation of a constant is 0. Okay. So half of 2x. So that's nothing but x. So you can see that this is showing you that this implies, this statement here is implying that x square by 2 plus c, this whole term, is the antiderivative of x. Okay. Let's try
Sir,
another example. Yes.
sir, so we will not substitute the value of c as 1.
C can be any value. Okay, so that is the meaning of it, that it can be any real number constant. Okay, so for example, x square by 2 plus 1, this is also antiderivative of x. इसका differentiation भी x होता है, but x square by 2 minus 10, इसका भी डेरिवेटिव x है ना, x square by 2 plus, for example, pi, where pi is 3.14, that's also x now. So that means c can take any numerical value, it can be any real number. So that is why actually this operation is called indefinite integration, because it gives me a constant which is indefinite. It's not a definite value. In fact, that is where the name indefinite integration comes from, because the constant of integration, this term c, it is an indefinite value. It has an indefinite value. So yeah, so let's just do one more example before we wind up. So n को अगर मैं half लेता हूँ, so that is I'm doing integration of x to the power half, or you can say I'm doing integration of root x. So according to this formula, how much it should be? It should be x to the power n plus 1 upon n plus 1 plus c. So that will become x to the power 3 by 2 divided by 3 by 2 plus c. So that you can see is 2 by 3 into x to the power 3 by 2 plus c. Now by a similar method, you can check later that this thing's differentiation will be this. Just like I've checked it for this case, you can check that differentiation of 2 by 3 into x to the power 3 by 2 plus any constant. It doesn't matter what the value of that constant is. It is going to be equal to x to the power half. So this term is the antiderivative for this term. So we are getting this term by integrating x to the power half. Okay, so understood this formula, na?
Yes, sir.
Yes, sir.
So I will tell you the exception also how to work that out. But first, just make a note of these two examples with the formula. It's going to be quite easy integration, because it's just like when we are doing an operation, it's just like the reverse steps of differentiation. When we differentiate x to the power n, we reduce the power by 1 and we multiply by n. When we integrate, we increase the power by 1 and we divide by n plus 1. So it's like, you know, we are doing a opposite kind of operation.
So antiderivative of n equal to half will be 2 by 3 x raised to 3 by 2, no?
Yes, 2 by 3 x to the power 3 by 2. That's correct.
Okay, sir.
You see, that's what we got here also, right?
So can you please read the last note?
Yeah. So the last one is telling us that differentiation of x to the 2 by 3 x to the power 3 by 2 plus c is equal to how much? X to the power half. D by dx of that bracket is with what thing? It is 2 by 3 x to the power 3 by 2 plus c. It is the antiderivative that we calculated from the formula, right?
Yes, sir, got it.
Okay, got it now.
So can we leave after writing this?
Yeah. Okay, so we'll conclude the session with this today, people. Okay. Don't know if you have another session today or not, but our session ends here. Okay, so I think we will have a regular timetable for this week, which means that again we'll have a lecture tomorrow evening in that case. Okay. When the timetable comes, we'll come to know. But anyhow, next lecture we will discuss the conclusion part of integration, some more formulae like integration of trigonometric functions, etc. And then some properties of integration, like we've done properties of differentiation. Okay. So it'll be quite easy, and we'll do some more examples of this thing also, maximum minima. Okay, so that's it for today's session, people. Wish you all the best. Thanks for attending.
Okay, sir.
Thank you, sir. Thank you, sir.
Please do not, and I'm writing.